All right. Take three. Third time is the best. So here's a question. What are the top reasons to come to San Diego? And anybody have any suggestions?
Sea lions.
Sea lions, that's a great answer. Maybe more general than that. I think Ilya suggested to meet people in Boston. Okay, so related to sea lions, I would say one of the top reasons to come to San Diego. Oh yeah, this is a long-standing open question. San Diego Zoo. At least that's what they tell you. Okay.
No, sea lions are better.
So visiting the San Diego Zoo. This is like a well-recommended thing. U.S. News and World Report, which I didn't even know had comments about zoos, and travelers almost unanimously agree that the San Diego Zoo is the best zoo they have ever visited. Some people. But I think a better reason is to come visit San Diego to see the Meta Complexity Zoo, which I'm going to be telling you about in this talk. Yeah, this is a niche joke about Columbia University's U.S. news ratings. Their zoo ratings have been improving dramatically. No one knows why. Okay, talk plan. Now that I've gotten that out of the way, we're gonna do like a very brief overview of like kind of the landscape around MCSP. Then I'm gonna give you a more in-depth tutorial on Chuichi's result on the hardness for partial functions. And then I'll give you a less in-depth tutorial on the hardness of MCSP with the random model. So this is my goal. Okay. And so now, US News hasn't seen this yet, but I'm going to tell you about the meta complexities here. So, in this workshop, you've probably seen a lot of different meta complexity problems. We saw time unbounded Kolmogorov complexity, time bounded Kolmogorov complexity. I don't think we've seen Levin's version of Kolmogorov complexity. We saw Allender's Kolmogorov complexity. We saw probabilistic Kolmogorov complexity. There's a lot of different versions of Kolmogorov complexity. And probably in a tutorial, this is a lot to keep in your head. So at least in the beginning, I'm just going to focus on our favorite problem, or at least my favorite problem, the minimum circuit size problem, which, it's the guy it's the meta complexity problem we grew up with, friendly neighborhood meta complexity problem. Later in the talk, we'll have some reason to talk about time-bounded Kolmogorov complexity more, but for now, focus on MCSV. Okay, so who here thinks that they could predict everything on this slide? So I'm just going to define minimum circuit size problem. Okay, no one is raising their hand? I guess I've been very surprising with what's been on my slide so far. So minimum circuit size problem, very natural problem. That's asking you to compute the circuit complexity of a given function. Maybe more specifically, you're handed the truth table of a Boolean function. So, I literally tell you on every input, this is what it outputs. This is a very long input. It's of length 2 to the n. Usually I'll let like capital N be the length of this truth table. And you want to decide, does there exist a size S circuit for F? And, to define this properly, you need to talk about what model of circuits you are using. In this talk, for the most part, we'll talk about the usual types of circuits with some caveats, which we'll see later. Another thing that we'll talk about later in the talk is partial MCSP, where you no longer say on each input what value you need to output. You might be able to put a star, in which case you just don't care about that input. And any circuit that agrees with all the 0, 1 values, that's good enough for you. Okay, any questions about the definition of MCSP? Okay. So this problem has a long history. Some would say it's older than time and space, and then they would cough and say complexity classes. It was defined, I guess, in the 1950s. Like the first paper on it is in 1959. The first accurate paper about it was in the 1960s, but that's another story. And so this is older than the time and space complexity classes, which, depending on what you think, are defined in 1965. What's the 59 paper? Yablonsky. So basically, he claimed to resolve P versus NP. I mean, P versus NP wasn't defined yet, but he would have resolved it. And yeah, there's a fun, or maybe not so fun story about that. If you want, I'll talk about it later. And I think what makes this problem interesting, and probably the reason like we're all here at this workshop, is it has like these seemingly special properties. In particular, if you could show it's NP hard, it kind of like extends the reach of P not equal to NP. So, if MCSP is NP hard, then P not equal to NP implies SAT is hard on average, it provides no natural proof of circuit lower bounds, you can't tackle NP poly, and maybe by the end of the week, one-way functions don't exist. So it seemingly has these special properties, if it's NP hard, or MCSP has these special properties, and if it's NP hard, we get a lot of nice stuff. Okay. I wasn't sure whether to put this on, but this is actually live footage. A depiction of describing MCSP's connections. Don't try this at home. This is professional. Okay, so the main open question, which you probably
Reference to the conspiracies paper.
yeah, not about that. Yeah, conspiracy. I love that title. Conspiracies between many algorithms. So the main open question is whether this problem is NP hard. It seemingly has all these special properties. If it's NP hard, that's really nice because it actually says like, okay, SAT also has these special properties. Just because if it's NP hard, they're pretty much the same problem. And we get some amazing consequences. So is this NP hard? And this is a question that like dates back all the way to like the birth of NP completeness, or at least Levin's version of that paper. And also, for a lot of the connections, it's important to understand the approximation version of the problem, which is, I kind of term like order versus chaos. And I think it's a pretty interesting question. It's one we could probably understand less about than the actual exact version of MCSP. Like, can you distinguish whether a truth table has like a really succinct description, like n to the epsilon, or it requires a very large circuits? And you could ask this question not just for MCSP, but whatever your favorite type. So now I'm just going to give a quick overview of what we know and what we don't know. And I don't want to try and be too exhaustive here because I want your attention span for the rest of the talk. But I think I'll say at least some of my what I think is most interesting about what we know. So what we know is we actually know that even though we don't know whether MCSP itself is NP hard, we know that a lot of natural variants of it are NP hard. So basically, like if you were to throw a dart to decide how to modify MCSP, we can probably show that that problem is NP hard. So if you replace circuits with formulas, we know it's NP hard, at least under sub-exponential time reductions. If you increase the number of output bits, actually, we saw this earlier in the workshop, you can also show that this problem is NP hard. You can define a conditional version. For now, it doesn't really matter what that is, but we'll kind of see what it is later. You can also show that this problem is NP hard. And what will be the focus of like the second part of the talk is you can even show it's NP hard for partial functions. So there's like a bunch of different versions of this problem, all of which we know are NP hard. Do you have a question? All right. Okay. About the problem itself, like one of the first things we knew about the problem is that like, okay, if crypto exists, one-way functions exist, then this problem is not in P. If you believe in, let's say, sub-exponentially secure one-way functions, then like MCSP doesn't have a sub-exponential time algorithm. And we also know like the best like proper hardness result for MCSP is that like SZK, this like statistical zero knowledge. If you know what it is, great. If you don't know what it is, it's just some cryptographically important complexity class. We know at least MCSP is hard for that complexity class.
Would it give you?
Oh yes, yeah, that's true. That's true. It should be randomized.
They write it as an open question at the end of the paper. I was wondering if you solved it during the time that I was absent.
Oh no, sorry, I was just rushed. Yeah, I'll do that. Yes, good. That should be randomized. And the second result we'll see later in the tutorial is like a little bit about how to prove it's NP hard for random walking. Okay, so that's kind of what we know. Maybe I don't know if anybody in the audience thinks there's there's some stuff I left out, but maybe if you have some favorite thing we know that you'd like to volunteer, that'd also be interesting. Okay, so I guess it covered it pretty good. All right.
Just a quick question to make sure I understand.
Yeah, sure.
You don't have to be hardness for some certain class of formulas.
Yes.
That does or doesn't apply to hardness for subclasses of formulas, like the DNF formulas.
It's true. It's tricky. Yeah. Because it's like you'll get one side but not the other. Because like if you have an upper bound on a larger, like if you know that there's a more complex circuit that does something, you don't necessarily know it. Yeah. So like so it's like really annoying because like you would think like one of the first results I guess proved in the 80s was that like DNF MCSP is NP hard. And you're like, wow, general circuits are way more powerful than DNS. Here's a problem that's hard on DNS. Of course, it has to be hard on general circuits, but yeah, we don't know how to prove that, which is crazy. Okay, so some things that we don't know relate to this question. We don't even know NP hardness. I mean, of course, we don't know. We know it for the formula version, but not the circuit version. But even if you go to like the babyest version of circuits, which I would say is like depth 3 circuits, we don't know whether the problem's NP hard. And depth 3 circuits, okay, we don't understand them super well, but I mean, we have like a decent understanding of them. It's not clear why this problem should be particularly hard. And what's really annoying about this problem in particular is like, we don't even have cryptographic hardness of this problem. Like at least MCSP, you know, we probably know it's not NP. This problem, like, yeah, there's kind of no evidence either way saying whether it should be hard or not. If you go to larger depths, like if you go to sufficiently large depth, then we know that it's probably hard, assuming, let's say, factoring is hard, but yeah.
So question about bounded depth. So this work about bounded depth cryptography is NR, that is construction of the PRG. I think it's what's the depth 3 or depth 4.
Okay, I'm not
There isn't a conjecture. Well, everything is when it comes to PRG, everything is a conjecture, of course. So there's a proposal of NR06, but I forgot. It's Reingold, someone now Reingold, I think. Conjecture of depth 4 objects, which is a PRG. So maybe it's not the depth 3, but I guess from that perspective, you said there is no cryptographic hardness. That would give you a big cryptographic hardness, because if you can do this,
so like, I mean, and that.
It's a little like depth 4 circuit.
So the natural way to prove that some version of MCSP is going to be hard is requires not just PRGs, but like PRFs. Like,
Yeah.
so like you're gonna need actually like a sub exponentially. Oh yeah, you're gonna need something that's like you can generate the whole truth table of the PRF and it should still be indistinguishable. So I believe in this setting this is not a very well understood question. Okay, but if you do go to higher depths, then we do have evidence. So yeah, like I mean this problem could be in P, which is kind of crazy. Okay, so we don't know much about that problem. Another thing, which was actually raised initially in this cabinet and side paper, okay, there's this problem MCSP. Maybe it's NP hard. I mean, at this point, I guess most of us guess it's NP hard. You can ask, does it have other properties that NP hard problems should have? So we know, because SAT has a search decision reduction, that every problem that's NP complete also should have a search decision reduction. And most of the time, if you take any, you know, problem that should be NP complete, it's like fairly easy to construct and see that it at least has a search decision reduction. But for the minimum circuit size problem, we don't know a search decision reduction. In fact, the situation is really bad. Like if you have like, let's say the decision problem is like in linear time, I don't know how to shave off anything for the search problem. And actually for formulas, we do know a polynomial time search decision reduction. And for some variants of, and you can make partial progress on this for like other variants of MCSP, but at least for MCSP itself, you know, we don't really understand the connection between the search problem and the decision problem. Yeah, but we have results that are like kind of in the neighborhood of that. If you're interested, you can talk to me and we can tell you more. Okay. Another thing is like, okay, we have all these variants of MCSP, which you can prove NP hard. You could ask like, okay, what kind of hardness of approximation should these things have? And like, I mean, at least the intuition from the cryptographic hardness is that like pretty much in the order versus chaos regime, all of these problems should still be NP hard. But even for these variants, like where we add multiple outputs or we consider partial functions, like our hardness of approximation isn't very good. So I think for both of these, the best hardness of approximation is logarithmic. Actually, this one we do have good hardness of approximation for. But it's kind of mysterious because it's like, okay, we've made the problem a lot easier, but we still can't prove good hardness of approximation. So it seems like we're still missing some techniques to even understand these problems. Okay, and then last thing, which Noam talked a bit about is called like the parabolic conjecture. One thing on this slide, I guess I forgot to talk about, was that there is like a slightly non-trivial circuit for MCSP. You can solve it. The naive algorithm would be like 2 to the capital N. And you can, instead of 2 to the capital N, you can get a circuit that's like roughly 2 to the 4/5 times N, up to lower the terms. But that's actually like a non-uniform circuit, and it seems to really require the use of non-uniformity. It's, on the other hand, if you want like a uniform algorithm, we don't know any way to beat brute force, which is kind of interesting. It's like one of the few problems for which this is true. And I mean, the other one that comes to mind seems to be like circuit stat. Yeah, so this is like kind of a summary of what we know and what we don't know about MCSP. Yeah, any questions? Okay, great. So that brings us to the second part of this talk, which is a tutorial about Shuichi's results. Shuichi, hopefully I don't mess this up too bad. Okay. Okay. Yeah. Okay, so we're gonna need two preliminaries for this. The first, I guess probably everybody will know, but just to review, there's this vertex cover problem, which is NP hard. Vertex cover just says, I hand you a graph and I ask you what's the smallest number of vertices that hit every edge. So for example, in this graph, if you just pick this one guy, you hit all the other edges. And in this graph, you pick these two guys, you hit all the other edges. So this would be the answer. Here was 1, answer here is 2. Vertex cover, good. Any questions? Nice. The second thing that I'm going to be vague about now and more specific about later is an encryption scheme. So for now, think of it as kind of a vague object that lets you kind of hide a bit unless you know a secret key. And the syntax of this is going to be, you're going to pick, the encryption scheme will have some secret key, which you'll kind of choose at random. You'll have a bit B, you'll want to encrypt it. There's some randomized algorithm that takes as input the secret key and the bit. It'll spit out a ciphertext random using internal randomness. And then you can also decrypt and get back the bit B if you have a secret key. Okay, encryption scheme. Good, and we'll eventually use some information theoretic encryption scheme, but for now, some object which has these syntactic properties. Okay, great. These are the two preliminaries. All good? Great. All right. So here's what the reduction looks like. Actually, the reduction is significantly more complicated than this, but I think this will illustrate a lot of the ideas. Okay, so we're going to reduce from vertex cover. What do? The first thing we do is for each vertex in the graph, we sample a secret key. Now, a secret key, you can think of it as a string of a certain length, but it's like, there's some parameters for the secret key that are associated with the encryption scheme, but let's not worry about them. Just sample a random secret key. And one thing to note about this is that this step is randomized. So this reduction is actually going to be a randomized reduction. It's not going to be a deterministic reduction, but we're perfectly happy with that. Okay, this is the first step. For each vertex, we sample a secret key. Now, what do I need to do? I need to come up with a truth table. So what is my truth table? I'm going to consider the following function. The function is going to take as input an edge, and really this is going to be like an index of an edge. So it's like, we'll have 2 vertices in it. So this is like 2 log n bits. And it's going to take it as input 2 ciphertexts. So the edge, let's say, will consist of the vertices v and w. That's what we'll call them. And we know which one's v and which one's w. And we're going to take in 2 strings that we're going to view as like purported ciphertexts. Okay, so these are the inputs to the function. And I should say it's going to be very important for this reduction that these inputs are going to be short. Because like we're going to want to consider the truth table of this function. The truth table is going to be of length 2 to the input, and 2 to the number of input bits. Describing an edge is cheap, that's 2 log n, we don't care about that. Ciphertext, it's going to be really important that these ciphertexts are short. Let's not worry about that for now, just some encryption scheme, but eventually in the back of your mind, you should be thinking, I want short ciphertext, but yeah.
Short mean like polylog or
Good.
O-log, or I just want.
Ideally O-log. If you want a polynomial time reduction, you want O-log.
Thank you.
But yes. Good. All right, these are the inputs to the function. So now what do we do with the inputs to the function? All right, this looks scary. What we're going to do, forget about this condition for a second. We're going to pretend the ciphertext is real, whatever. I mean, it's an arbitrary string, but we're going to pretend it's a proper ciphertext. And we're going to decrypt using the secret key associated with V. So in the beginning, we picked a secret key for every vertex V. V is, let's say, the first vertex in this edge. Now it has some secret key associated with it. The output of this function will be the decryption of this ciphertext using that secret key. Okay, that's that part, hopefully clear. Now let's look at the second part. The second part, what it's saying is both of these ciphertexts encrypt the same bit. So it's saying if you decrypt the first ciphertext using its corresponding secret key, it's equal to the bit you get if you decrypt the second ciphertext using a corresponding secret key. So it's saying these two things encrypt the same bit. And so another way to write this is it's like you have to output the bit B if that is encrypted, assuming both encryptions are encrypting it to the same bit. Okay, there's a lot of notation up there, but hopefully it's clear. It's basically like some sort of, you're given an edge and a ciphertext for the vertices in that edge. And under the assumptions they decrypted the same thing, you want to output that decrypted value. Marco?
Does this mean that whatever circuit is gonna come out of this is gonna have to memorize the secret keys for all the vertices?
Very good. So what you'll want in the end, and we'll see, is that you're going to want to memorize all the secret keys corresponding to a vertex cover. That's what you'll want. But we'll get there. Okay, good. All right, we're like 2/3 of the way done. We're literally going to say you can output whatever you want in any other scenario. We only care about what happens when the two ciphertexts are encrypting the same bit. Otherwise, you can do whatever you want. And this star case is going to be really important because, like in the proof, what's going to happen is we're going to get a circuit that satisfies this condition, and it's going to do something we don't understand on the star thing. What's going to happen is we'll look at what it's doing on the star things. We'll look very closely, and we'll say, oh, it's doing this. That must mean this must be in the vertex cover. It's doing this. Must be this is on the vertex cover. So it turns out like the behavior of our circuit on the star inputs is what we're going to use to extract out a vertex cover later. Okay. All right, so this is the function. Any questions about the function? Great. All right, so now what are we going to output? Our goal is to estimate the size of the vertex cover. And our estimate for the vertex cover is, we're given an oracle to partial FCSP. So we construct this truth table. We look at its circuit complexity, and we divide it by the size of the secret keys. So if like you're into, one way of solving this is to memorize all the secret keys. And it turns out what we'll do is, and you can actually smarter, as we'll see in a second, you actually only memorize the secret keys in a vertex cover. And it turns out that's going to be like the dominant term in constructing the circuit. So it's like, this is going to be our estimate. Okay, now I'm going to tell you, go over the upper bound and the lower bound, but does everything make sense so far? Great. Yeah.
If you come back to this, why would that be an approximate size for the vertex cover?
Yeah, okay. Well, maybe give me 2 minutes, and then if it doesn't make sense, then. Okay, so how do we argue the upper bound? So let's say we have a vertex cover. Let's say these two vertices. One thing you could do is you could memorize the secret keys corresponding to those vertices. And then you can decrypt using them. So now you're given an edge. And then you're given two ciphertexts. You're given an edge, and you memorize one of them, because it's a vertex cover, you memorize one of the two secret keys. So then what do? Decrypt using that secret key. Now you might not know if this condition is satisfied because you don't know the other secret key. But either it is satisfied, in which case, you got the right answer, or it's not satisfied, in which case it's a star input. So who cares? Okay, did that make sense? Okay, so does everybody agree? Okay, I'm lying here. This isn't actually less than or equal to, but it's like roughly less than or equal to. Okay, good. And of course, you can set parameters such that, because everything I talked about here is fairly efficient as long as decrypt is efficient. Really, as long as you make the secret keys very large, that's all that's going to matter in your script. Okay, nice. Now the lower bound. Now in the lower bound, remember I was being a little bit vague earlier. I said here's an encryption scheme, but I really just defined some syntax for you. Now we're going to have to use some property of the encryption scheme, which I haven't defined yet, but we can talk about it formally, and then on the next slide I'll define it formally. So what we're going to do is we're going to use a quote-unquote extractable encryption scheme. So what does that mean? It means this. Somehow, we're going to take a circuit that computes this function, and then we're going to extract from the circuit one secret key from each edge. So we'll look at an edge. There'll be two vertices there. And then we're going to run some procedure that will literally analyze the circuit and then spit out a secret key for one of those two vertices. And then assuming we can do that, then we can also get the lower bound. Well, okay, okay. The idea is now I have a secret key for each one of the two. For each edge, I have at least one secret key. So that means I have a vertex cover basically of secret keys. And because these secret keys were chosen uniformly at random, there's no shorter description for it than just, outputting, than just the length of it. So roughly the circuit size needs to be greater than or equal to the length of the secret keys times the vertex cover. And this is just information theoretically because I picked these strings at random, so any way for describing them isn't going to be much shorter than their length. Yeah.
I'm sorry, I'm confused. So far, I saw you use the star once.
Yep.
To avoid having to explicitly check that condition.
Yep.
Are you gonna use it again?
Yeah, it's going to be in this extraction step. Any other questions? All right, great. All right, so now I'm going to tell you what this extractable means, and then I'm going to tell you how you extract. Okay, but just to review so far, we have a function, take as input an edge, two ciphertexts. You need to decrypt, assuming the ciphertexts are equivalent, I guess. Yeah. And we saw an upper bound, which is just memorize secret keys in a vertex cover, and that suffices because you only have to decrypt when the both ciphertexts are equal. Now, if you have some extractability property that pulls out a ciphertext for each edge, then you get the desired lower bound. Okay, Ilya, now is it clear that circuit size should be proportional to vertex cover size?
This is probably like the expectation, since you mentioned this is the shortest possible description.
Yep. Yeah, it's a randomized production. Okay, good. So what is an extractable encryption scheme? Extractable information theoretic encryption scheme. So I'm going to give you an example of one, and then I'm going to tell you what extractable means. And this example might be meaningful for those of you who know Goldreich-Levin. If you don't know Goldreich-Levin, it doesn't matter. It's just some example. So here's an example of an extractable encryption scheme. It takes the bit B. In order to define the encryption scheme, I need to tell you what this encrypt function does. It takes as input a secret key, takes as input a bit, and it has some randomness. What it's going to do, its ciphertext is going to be the randomness for the encryption algorithm, so it's just some random string. And then it's going to be a one-time pad, or I guess it's not a one-time pad. You're going to pad the bit B with some inner product of the secret key with R. This is just, if you haven't seen Goldreich-Levin, it might be like, why the heck is this a reasonable thing to do? But I mean, at least it makes sense. You just, you're XORing the bit B with, something associated with the secret key, and that's your ciphertext. If you know Goldreich-Levin, after I tell you something in a bit, you'll kind of see why this thing should be extracted. Okay, example makes sense. Good. Okay, here's the extraction property. We want the following. We want that there exists an extractor E. And in fact, for this argument, an extractor E is just some algorithm. We actually don't even need that it runs in polynomial time. It just needs to run and it needs to halt. So it's just some algorithm called the extractor. And we want the following. If you can break encryption, that will imply, and I'll define what this means in a second. If you can break encryption, then that means you must know the secret key. That's what we want the extraction property to say. How do we formalize that? If an adversary is able to distinguish the following two distributions. In the first distribution, I have a bit B and the encryption of that bit. In the second distribution, I have a bit B and just a random string of the appropriate length. So here, actually, this is just uniformly random bits. Here, these corresponds to decryptions and ciphertexts. Okay? And in particular, if you're able to break encryption, you should be able to distinguish these two things. So this is a formalization of breaking encryption. Great. Okay, what does knowing secret key mean? It means precisely that this algorithm E, if you just feed it the code of A, it's able to pull out the secret key. I'm lying a little bit here, but yeah. You'll actually need like some small bits of advice, which correspond to like the advice in Goldreich-Levin, but whatever. Okay, is the definition of extraction property clear? So if you can distinguish encryptions from random, then you can actually extract out a secret key. And if you think about the Goldreich-Levin algorithm, what basically, if you're able to distinguish these two, then you go distinguisher to predictor, you can predict this thing, and then you use Goldreich-Levin, you can extract out a secret key. You'll need a small number of bits of advice, which I swept under the rug, but that's it. Yeah.
So E also needs some access to like the actual, something involving the secret key, right? So is that, what kind of access does it get?
It doesn't need to know the secret key. That's where it'll actually get a small number of bits of advice for the secret key.
Oh, no, I just mean like, the expression at the bottom of the left-hand side doesn't depend on the secret key, right? So,
This expression.
yeah, well, on the left-hand side.
This,
No, just E of A itself has nothing to do with the secret key, right?
yeah.
Because A is just an algorithm that can run on any secret key. So,
All right, let's not worry about it.
okay.
Okay, this is an extractable encryption scheme. Okay, so now I want to explain to you this kind of informal part. And when we talked about the lower bound, we said, okay, we're gonna use an extractable encryption scheme, then we're gonna extract from the circuit one secret key from each edge. How are we gonna do that now that we have extractable encryption scheme? All right, what are you gonna do? This is our goal. We look at the circuit and we want to extract one secret key from each edge. So we do the following. So let's say you hand me a circuit that computes this function. I've just restated the function here. I'm going to do the following. Consider the following random variables. I pick a bit uniformly at random. I have a ciphertext for that bit with the corresponding secret keys. And also, let's say I also have some uniform randomness R. These are just some random variables. And I consider what happens. Let's run the algorithm A on the edge, the proper cipher encryption of that bit, and the proper encryption of that bit. Okay? So what do I know about this? Well, by the definition of the function f, it should spit out the bit. If I give it encryptions, the same encryptions of a bit b, it should output the bit b. Okay? Great. So now let me run another experiment. And really what I'm doing here is a hybrid argument, but let me run another experiment. Now let's, instead of giving you the proper ciphertext for b, let me give you a random string. Okay? Put a random string, then I can look at what the adversary does. I don't know what the adversary does. Maybe it does roughly the same thing, maybe it doesn't. I don't know. Okay, we run another experiment. Now I give randomness for the ciphertext of V and also randomness here. Again, I don't really know how this compares to this. I don't know. But I claim now you're probably not equal to B. At least with probability half, you're not equal to B. And the reason is R of V and R of W, they're just uniform randomness. I picked B uniformly at random, completely independent from that. So this is not equal to B, at least with probability half. So in the beginning, I was equal to B. At the end, I'm not equal to B. So at some step here, these two things were distinguishable. I don't know which step, but one of those two is distinguishable. So by the extraction property, I can either recover the secret key associated with V. That's the case where I can distinguish a ciphertext for V from random, or I can just recover a ciphertext for a secret key for W in the case that I can distinguish these two. Good. Okay. Nice. All right. So that's as the deep level of detail I want to go into with respect to this reduction. On the next slide, I'm going to talk about like extensions and open questions. But any questions about the reduction and the intuition for it? Yeah.
At this point, is the star a flag for the random case that you're not equal to B?
Yeah, you can think about what's happening is like the stars are somehow telling you this is the stars are letting you run the circuit on like they're letting you tell whether or not he's the value of the circuit on stars is telling you extra information. And what this step is doing is it's letting you tell whether or not this guy is memorizing the secret key for V or the secret key for W. So that extra information, you can think about it is like, I mean, if you look at like what Noam talked about in terms of like Levin reductions, it's like the way you pull out the witness, the vertex cover, is by looking at behavior on the stars. If the stars weren't there, you have no idea what, or it's like not clear what. Yeah. Okay, any other questions? Okay, great. So some extensions and questions, open questions. One is like the most natural question is hardness for MCSV. Okay, and in particular, can we remove the stars from the reduction? So the only place where the stars are coming from the reduction is because we need to handle this case where the two ciphertexts are not encrypting the same bit. So, I mean, if you could come up with an extractable information theoretic encryption scheme where somehow you're able to tell on two independent secret keys whether they're encrypting the same thing or not, then you'd be in business. But that seems kind of implausible. Not implausible, but like at least I don't see how to do it. But maybe there is something very clever you can do to somehow handle this case where the ciphertexts are not encrypting the same thing. Okay, so that's one question. Another question is you're saying, okay, fine, we have this reduction. Forget about the reduction. Don't try and fix the reduction. We have the reduction. now we know that partial MCSP is NP hard. Maybe there's some way of transforming an instance of partial MCSP into an instance of MCSP. Maybe there's a partial to total reduction. And in fact, we know such a thing exists for formulas, which is how we get that the formula version of MCSP is NP hard. But as partial to total reduction, we don't know it for circuits. And yeah, in fact, and it's worth noting the partial to total reduction formulas ends up like using some very simple lower bound techniques. The idea is like this leaf weighting technique of Buchführer and Umlaut. So it's, I don't know, it's plausible that the circuit world that you could use some very simple lower bound technique in order to get a partial to total reduction. But you don't need to, you might not necessarily have to prove some high powered lower bound. You just kind of need like a sufficiently nice, but maybe not super technically challenging lower bound. It's like a very, so that's another question. Okay. The other thing is better hardness of approximation. So, okay, this presentation of this result is kind of painful because it removes one of the most beautiful things about this result, which is, and I apologize, which is secret sharing. It turns out in order to get the best hardness of approximation, not necessarily for this problem, but for some related problems, like if you're allowed to put more stars in the truth table and stuff, you want to use secret sharing in like a very cool way, and it's like a really cool application of cryptographic ideas. And so that will give you better hardness of approximation for some related problems. Although, yeah, in this case, for partial MCSP, the best hardness of approximation, and Shuichi, correct me if I'm wrong, I think is like roughly logarithmic, slightly less than logarithmic, right? And I mean, okay, this problem seems way harder than logarithmic hardness of approximation. It would be extremely hard, hard to approximate. So for better hardness of approximation of this problem, I don't know. And it's not clear to me why there should be a barrier for doing this or not. I don't know. Shuichi, you have any intuition? You think that there? No, okay. Yeah, you're not sure.
Question, so should you really different way of proving this result?
Yeah.
I don't know if you would discover.
Yeah.
So can you continue with this outline and like finish the actual proof?
So, okay. If you replace vertex cover here with set cover, you could, yeah, well, vertex cover, the problem is it only has hardness approximation like 2-factor. And set cover will have like log of hardness approximation. Then you can basically recover Shuichi's result. Like the reason you need to use minimum monotone satisfying assignment is to get better hardness of approximation for other problems and related problems. But as far as I can tell for partial MCSP, you actually don't need like the full strength of the secret sharing and the full strength of minimum monotone satisfying assignment. So actually, I think the vertex cover, like, okay, what you could do is actually, instead of vertex cover, you go to hyper vertex cover, and then you'll recover Shuichi's result without it, yeah.
And like shrinking the size of encryptions and all that.
Okay, good. So here, shrinking the size of the encryptions, oh, I guess it's the previous slide. So here, in the example, I talked about Goldrake-Levin, but actually, if you want the encryptions to be small, what you really need is some like reconstructive PRG construction. So instead, so you want a reconstructive PRG constructor with short seed length. And then Goldrake-Levin, which roughly corresponds to direct product generator, is bad for you because it has long seed length. So what you want is something with short seed length. What has short seed length? Nissan-Wigderson. So you use Nissan-Wigderson here instead. Now you get the short ciphertext and you're good. Well, okay, there's more you have to do, but yeah. But yeah. Okay, any other questions related to this partial MCSP result? Yeah.
Yeah. If suppose you get an encryption scheme that does satisfy the property you want, so
Sure.
you can remove the stars. Does this reduction also avoid all of the possibility results of like you can't prove NP hardness of
Well, okay, so like if you talk about no stuff about Levin reductions, it would have that, well, the way that it would avoid that would have to be inside the information theoretic scheme. The Sachs-Sampson barrier, yeah, I mean, the Sachs-Sampson barrier seems to suggest that this encryption scheme doesn't exist,
okay.
but yeah, yeah, that would be my guess. I mean, I haven't thought about it very carefully, but yeah, okay. Okay, great, and these are great questions. Any other questions? Great. So next I'll talk a little bit about this random oracle results. I'll probably go into less detail about this. Let's see, how are we on time? When did we start? Did we start? Or, okay, when should I end?
Yeah, we started 11:10, so we're bumped 10 minutes.
Gotcha.
To the end time, which
12:10.
12:10.
Yes. Okay, so now I'm going to tell you about this random, no, it's fine, random oracle, hardness result for MCSP, or you could think of it as like, gives you some candidate, entropy hardness reductions. And so, at least the way I try and summarize this is, okay, what's the problem? Anybody have any guesses as to what the problem is? The problem, sorry for photographers in the audience, is one-way functions. I think one-way functions are great, but as you will see, they're a problem for us. But the solution, anybody have a guess for what the solution is?
One-way function.
Solution is one-way functions. One-way functions are great. They're going to be the solutions for us. Great. So, and yeah, and it's nicely summarized in our friendly neighborhood meme. Okay, so I'm going to talk about something that seems completely unrelated, but will be related soon. So there's this fact in information theory, which is called symmetry of information. And there's basically this quantity mutual information. Doesn't really matter how it's defined for now. But it roughly says the information that a random variable reveals about another random variable is equal to the vice versa. And it turns out an equivalent way to write it in terms of entropy is like this. Okay, that's a statement about information theory. This workshop's not about information theory, it's about metacomplexity. So you can ask, is there an algorithmic version of symmetry of information? And in order to ask that question, you need an algorithmic measure of entropy. Luckily, there's this very nice definition, which is time-bound Kolmogorov complexity, which you could think of as some sort of algorithmic measure of entropy, because entropy is talking about how many bits you need to describe something. Time-bound Kolmogorov complexity is also talking about how many bits you describe something. So in particular, I guess probably everybody knows this by this point, but the t-time bounded Kolmogorov complexity of x given y is the minimum length of any t-time program that outputs x on input y. Okay, any questions about this? Great. So now we have an algorithmic measure of entropy. We can ask the symmetry of information hold. And one of the first results, or one of the, I guess maybe not the first results, but one of the foundational results about Kolmogorov complexity in the time unbounded regime, that's what the infinity is up there, is that symmetry of information actually does hold up to basically additive logarithmic terms. So in fact, yeah. Okay, great. But that's an unbounded amount of runtime. This isn't a computability workshop, it's a complexity workshop. So you can ask, does this hold when we talk about properly time-bound complexity? And if so, I can just like rearrange the terms here. I could put this guy on the left-hand side and this guy on the right-hand side. It would say like the conditional complexity of some strings can be related to like the unconditional complexity of related strings. And that turns out to be a win condition for us because we actually already know this problem is NP hard. Actually, this is lying a little bit. We only know it's hard in a specific case that this actually doesn't apply to, but you can fix it. So if we could just show symmetry of information, then by reducing to a result we already know, we would win. Okay? So it doesn't really matter what's on this slide. What you need to remember is symmetry of information implies win. Great. Unfortunately, the answer to this question is no. Does anybody have an intuition for why that answer to the question should be no? Great, one-way function. As the Spider-Man meme predicted. So you can imagine, let's say a one-way permutation, just because it makes the proof easier, although it's true for one-way functions. If you have a one-way permutation from n bits to n bits, you could look at the following scenario, one where you pick x uniformly at random and y from f of x. And the hope is that the time-bounded Kolmogorov, we have this statement. But okay, so what's the first term in that? What's the complexity of describing x and y? Should be n, great. Because you describe x and the code for f, then you just use x, y, so that's like roughly n. What about, what about y? Well, you pick x uniformly at random, but it's a one-way permutation. If I only tell you y, that's uniformly at random, that should be n. Now, what about this guy? Well, if it's sufficiently one way, if I tell you y, in order to get x, you have to invert the one-way permutation. That seems pretty hard. So maybe that's also like roughly n. And I mean, it depends what setting you're in, whether n is approximately 2n, but in our setting, that's bad. So no, symmetry of information is false. This is some intuition. You can formalize it assuming one-way functions exist. Okay. We have our problem, yeah.
Which then we do if you assume there are no one-way functions.
Oh, that's a good question. In fact, there, yeah. So you can prove some statements of the form. If there are no one-way functions, then some version of symmetry of information holds. But like there are some like technical, well, we can talk about it later. Okay. So what is the result? It turns out if you don't hold, so symmetry of information implied win. Unfortunately, symmetry of information is false. So you come up with some definition that is actually a relaxation of symmetry of information. And you show actually that suffices to win. And at least it's a reasonable assumption in that it holds in the random oracle model. What is the random oracle model? Actually, let's not worry about that yet. Okay, good. And this resolves some conjecture that we made with Yiji Huang and Hunlin Ren, that MCSP is hard in that random oracle model. And in particular, because we have, at least the cryptographers believe we have candidate functions that look like random oracles, you get candidate NP hard distribution. Okay, this is like a quick high level idea. Okay, so what is this relaxation? So we have this problem, the one-way functions were killing us. Can this be fixed? Okay. And so there is kind of like a general idea that's like used throughout computer science, which is like at first you don't succeed, try, and this holds very broadly. I don't know. Okay, if that is a very general technique, it helps a lot, as we saw in Rocco's talk. But okay, that's not our technique. It's a very good technique. But, what we need is if at first you don't succeed, try. Okay, it's true. If at first you don't succeed, trying the complexity juncture, as Marcus suggested, is a very good thing. That's a very powerful technique, which you should try, but it's not. For our case, what we need is if at first you don't succeed, try boosting something. Okay, as we saw yesterday, boosting something is also a very good technique, but what we need in our case is if at first you don't succeed, try encoding differently. Okay, what does that mean? The idea is the relaxation is this definition called pseudo-symmetry of information. So it's true we couldn't have symmetry of information hold for X and Y. Instead, we're going to hope for something else. We're going to hope that maybe pseudo-symmetry of information holds when I encode Y in an appropriate way. So I'm allowing to do some post-processing on Y. And after the post-processing happens, then I hope some symmetry of information holds. That's kind of the idea. Let me describe it in more detail. Okay, so let's think back to our example with the one-way permutation and kind of use that as a test case for understanding what pseudo-symmetry of information needs to do. So we had this one-way function, which mapped X to Y. We were imagining the case where you pick X uniformly at random and then map to Y. Now, what I want to add on top of this is some encoding step. In particular, this encoding step is allowed to be randomized, and the randomness can be very, very large compared to X and Y. So there's some step which maybe takes a lot of time, but like still polynomial amount of time, which will map Y to Y tilde. And I want it to be encoding in the sense that from Y tilde, you can go back to Y very efficiently, and let's say deterministically. Okay? So it's an encoding step. Basically, you can think about it as like injecting randomness into Y, but we'll still let you decode back to Y. Okay? And then what I hope for is that now symmetry of information holds, and that like the complexity of X and Y tilde is going to be like roughly the cost of describing Y tilde, and then the cost of describing X given just the original Y. Okay? And you might wonder like what the heck is going on? Like it seems like the problem here had nothing to do with encoding or something. Like why would encoding the string Y get around this attack? And somehow like the idea here is like, you might think that Y tilde isn't that different from Y, but the core idea behind this is like somehow pseudo randomness and incompressibility are not the same thing. So like in this setting, what we care about is incompressibility, because that's how time-bound and Kolmogorov complexity is defined. Whereas like you might like this, while the string Y tilde is not pseudo random, and because it like always decodes back to Y, so it's like very much not pseudo random. It turns out it does have a very strong sense of incompressibility. And so this distinction between pseudo randomness and incompressibility, which is actually like doesn't exist in information theory. In information theory, they're the same thing, but at least in the computational world, they're different. And this is like related to like Yao pseudo entropy versus Hill pseudo entropy. That's kind of some intuition for why this encode step is actually doing something useful for you. And so at least one direction here should hopefully be clear. Like if I want to describe x and y tilde, I can describe y tilde. And then if I have described y tilde, I can run decode to get y back, and then I can describe x given y. So that should be clear. The other direction is less clear. You have to work for it. But it turns out you can show that at least in the random oracle model, this thing is true. And I don't go into the details of the construction because I don't think I have enough time, although I do have slides on it if you're interested. Kind of what the oracle does is it's like breaks up y into chunks and like finds a random pre-image of the oracle under that y tilde. It's it has to do a lot of rejection sampling. It actually resembles very closely a proof of work. But it turns out using this idea, you can show that time-bounded Kolmogorov complexity is NP-hard in the random oracle model, and then building on that, you can also show MCSP's NP-hard for bit. Good. So this is the level of detail that I was going to go into with respect to this result. I do have more slides if you want more detail. But is there any question about, yeah?
Very last thing that you mentioned, so I'm just wondering, what would be the counterpart of this symmetry of information or pseudo-symmetry or any one of those when you replace this KT with MCSP? So
Yeah.
you don't prove, I guess,
Yeah.
or is it you prove NP hardness for that and then you move from KT to MCSP? I guess you don't get anything like that
Yeah.
for MCSP
Yeah.
explicitly.
Yeah, very good. So yeah, like this idea of pseudo-symmetry of information, it's like not clear what it would mean for circuit complexity. But it turns out if like you just take the reduction that worked for time-bounded Kolmogorov complexity and plug circuits into it, the reduction still works. So yeah, I don't have a nice high-level version of that, but okay, great. So thanks for listening. Just some questions that I think are really nice. I mentioned some of these before. You know, is MCSP NP hard? Can you remove the stars and here hardness reduction? Do this partial total reduction. Another thing is like ETH hardness of MCSP. Like the person to ask about this is Marco, who has been, you know, we know ETH hardness for formal MCSP, and there are like some ideas for potentially trying to do this for MCSP under ETH hardness, but at least from Marco et al. Results, seems like maybe that approach is what we maybe did. I don't know. It's doing okay. Doing okay. Okay. Yeah, I think another really nice question is hardness approximation for partial MCSP. Like we already saw such beautiful ideas going into this hardness approximation that gives us like slightly sub-logarithmic hardness approximation. I don't know any barriers for getting like, I don't know, n to the epsilon hardness approximation. That should be a really nice question. And I think it should involve some beautiful ideas. Related to the random oracle stuff, like can you get hardness under other cryptographic assumptions besides random oracle? Even just like, unfortunately, the way the proof uses the random oracle, it uses it in multiple ways. There's this step where I told you I was lying about like the hardness of conditional time-bound Kolmogorov complexity. Turns out you use the random oracle there as well. So now it's using the random oracle in like two ways, and it's like really annoying the ways that they combine. And so like we don't have like I can't like give you a list of nice properties that if a function satisfies it, then this reduction goes through. It'd be nice to better understand that. Or, you know, like, I mean, the dream would be, or at least one thing that would be nice is like, you know, if you could show one-way functions imply NP hardness and MCSP or something like that, that would be really amazing. Another thing is even in the random oracle model, it turns out you get like the hardness approximation you get isn't as good as you'd like. Okay, so you get actually like basically optimal additive hardness of approximation, but multiplicatively you don't get much. So that's another nice question. And yeah, the last thing maybe that I didn't talk about so much in this talk, but like depth 3 MCSP, like what the heck is going on with that? You know, it's so close to depth 3 formulas. Like depth 3 formulas and depth 3 circuits are only like a factor of little n apart. We know that depth 3 formulas are NP hard, but we don't know with large enough approximation that we can get depth 3 circuits are hard. So it's like, what's going on? All right. Thank you very much. Yeah.
Number 4.
Yeah. Okay, so if you think about pseudosymmetry of information, kind of like in its definition is like it has a very additive nature. And if you like throw multiplicative factors in here, you like kill everything. Because like if you remember, okay, before I said like n not being equal to 2n is really bad for us. So it's like, yeah, it seems like this approach doesn't seem to be the right approach to do multiplicative stuff. So like, okay, it seems like a very powerful function, it's a random oracle, right? Like, you should be able to get really good hardness approximation.
You don't have any barriers, different ways.
No. Yeah, in fact, for any of these results, any of the known results, it's not clear to me, what barrier there is to getting better hardness approximation. So the one example where we do know better hardness approximation is like the conditional version of MCSP, for example. And there, the idea was, okay, we were doing these like kind of similar vertex cover, set cover things. And then the idea was, you actually had to do some really cool stuff, which was like, there's this result that witness encryption exists in the generic group model, or sorry, the generic multilinear map model. And then if you implement that in the oracle, then you get this. So it's like, you needed some really powerful crypto statement in order to get the best hardness approximation, which to be clear is unconditional because it's put in the oracle. So I don't know, maybe you need to use some even more cryptographic ideas. I don't know. But great. Any other questions?